Okay, took our break a little early this time because it made sense to stop after the quiz. All right, so let's talk about the Wittig reaction. The Wittig reaction is one of those reactions that when I was taking organic chemistry, I didn't recognize its importance. It's a carbon-carbon bond forming reaction, and carbon-carbon bond formation is among the most important things organic chemists are trying to do to build up large molecules from small molecules. So I didn't recognize how important this was until I'd gotten it wrong on a quiz and an exam and on the final. And then I thought, maybe I should have learned that Wittig reaction. It seemed expendable at the time, but it's not. And the key with the Wittig reaction is it converts a CO double bond to a CC double bond. The other things that are attached can vary, but the key is converting a carbon-oxygen double bond to a carbon-carbon double bond. And so it's kind of powerful because once you have this carbon-carbon double bond, you can also add things across it. You can reduce it to make it a carbon-carbon single bond. So it's a very useful reaction from that perspective. The problem with the Wittig reaction, there are several problems. It has what we call poor atom economy because one of the reagents for the Wittig reaction is triphenylphosphine. And triphenylphosphine has a lot of atoms, and none of them are incorporated into the products. You end up throwing away a lot of waste, which is kind of bad for an environmental perspective, but it's also bad from a cost perspective because you've got to buy this stuff. You're paying for all that carbon, and then you're just pitching it. The other problem is difficult separation at the end. Because the triphenylphosphine becomes triphenylphosphine oxide, triphenylphosphine oxide is nonpolar. It's organic soluble. So the waste product in the case of the Wittig reaction can't be just washed into an aqueous layer and flushed down the sink. And that's usually what we do. Well, not down the sink anymore. Right now we dispose of things properly. But in the old days, you used to just put it in the aqueous layer, pitch it down the sink. This is really hard to separate from your product. And it has a high molecular weight, which means there's often more of it than of your product by mass, right? So you're trying to get rid of something which has very similar polarity properties. You can't really chromatograph it away very well. Similar solubility, so recrystallization is a problem. Distillation might work if your product is volatile because this isn't, it's a solid. But you're trying to get rid of maybe 5 grams of material, which is your byproduct, for 2.5 or 3 grams of product. So you got a ton of this, and it's a nice white solid, so it looks like your product until you take it in more, and then you realize, shit, I just isolated my byproduct and threw away everything I was looking for. So that's a problem, and it is not very stereoselective. Which means that you get a mixture of E and Z isomers around the double bond. So there are other more modern or more recent developments. None of this is recent, right? This is all done probably in the 1920s and 30s. But the Wittig reaction is the first example of using a phosphorus alate. But it's not the best example. So after we've introduced the Wittig reaction, which is one we covered in your text, I'll tell you about the Horner-Emmons reaction, which is actually a better way of accomplishing this. It has better atom economy. Purification is simple because the white product becomes water soluble, and it is much more stereoselective. The advantage of the Horner-Emmons reaction is also that it has the opposite stereoselectivity. Whereas the Wittig reaction tends to give primarily the Z isomer, although not very well, the Horner-Emmons gives primarily the E isomer. So you can change the conditions and change which product is the predominant product. So the key is the nucleophilic acyl addition reaction. And the key is figuring out what's actually the nucleophile. And the nucleophile is the aforementioned phosphorus ylide. And an ylide, in general, is a molecule with a positive and a negative charge on adjacent atoms. So in this case, since it's a phosphorus ylide, the adjacent atoms are going to be a positively charged phosphorus and a negatively charged carbon with a lone pair. And then there's other stuff attached. In the case of phosphorus, it's that triphenyl. So making the ylide happens before the carbonyl compound even gets to play. One of the challenges with the Wittig reaction is that the carbonyl compound, which is the compound you're doing the nucleophilic acyl addition to, isn't even part of the reaction until step 3. And you really want to start using that carbonyl compound because you have it and you're fixated on it, but you need to wait. The carbonyl compound doesn't do anything. So the initial step is to take that triphenylphosphine, because it has a nucleophilic lone pair, and react it with an alkyl halide. And I've shown you several different ways in the course of this of how to abbreviate that C6H5 group. So that's the phenyl group. And that's the same as saying C6H5. And that's the same as saying pH for phenyl. And it's also abbreviated with the Greek letter phi. So anytime you see any of these 4 things, those are interchangeable. So I'm just going to show this as phi3p. And then we're going to react this with an alkyl halide. And let's just use bromoethane as an example. So this is an SN2 reaction. And it's a really good SN2 reaction. Positive charge on phosphorus now because it now has 4 bonds and no lone pair. It goes with inversion of stereochemistry, not that that matters. To form a phosphonium salt. In this case, phosphonium bromide. Phosphorus chemistry is mildly annoying because there are a whole bunch of different possible phosphorus-containing species, and they've all got names. Right? So this is a phosphonium bromide. We've converted a phosphine and a phosphine is a phosphorus attached to 3 carbons sometimes. So this is triphenylphosphine. So the first step has nothing to do with nucleophilic acyl addition. It's just an SN2 reaction. Why is this such a good SN2 reaction? Who remembers from last semester what it is that makes phosphorus a really good nucleophile, better than nitrogen? Just checking your text thread, see if anybody put anything in there. Why is this a better nucleophile than the corresponding nitrogen? You can answer that in one word, if it's the right word. You want a hint?
Does it have to do with the electronegativity?
That's a good word, but not the right one. Nitrogen is actually more electronegative than phosphorus, which makes it a slightly better base. So it's not electronegativity in this case. So it's a different word. It begins with P.
Oh,
Polarizability.
Polarizability. For neutral nucleophiles, right? Polarizability is a big factor. For negatively charged nucleophiles, it's basicity, right? But for neutral nucleophiles, it's polarizability. So the triphenylphosphine phosphorus lone pairs in general are excellent nucleophiles in neutral solution. And you can run this reaction in a variety of different solvents. Pretty straightforward. As you might imagine, because these two hydrogens are adjacent to a positive charge, they're relatively acidic. Right? A negative charge on this carbon would be stabilized by the presence of the adjacent phosphorus. So we can take that off with a strong base. And the most common base is N-butyllithium. And you can buy solutions of N-butyllithium stored in a bottle under argon so they don't react with water in the air, often as a 1.5 or maybe 1 molar solution in hexanes as the solvent, right? Nice hydrocarbon solvent. So this lone pair, this is about 40% ionic, which means there's significant negative charge on the carbon. This pair of electrons is going to yank one of those hydrogens off and make your delete. So step one, just an SM2 reaction, nothing you haven't seen before. Step two, form the ylide by taking that proton off. And the other product is butane. Which just evaporates out of the solution, right? It's just a gas, it's irrelevant. So we've got the other product of lithium bromide, right, which is going to go into the aqueous layer eventually. So we've made that ylide. As you might imagine, you can write a resonance structure for that. And that resonance structure that has the double bond between the carbon and the phosphorus is called a phosphorate. Right? So there's this ylide phosphorate resonance. Phosphorus can expand the octet. And the phosphorate avoids charge separation, so it's actually the better of the Lewis structures. Remember great rule of organic chemistry number 1? What's great rule of organic chemistry number 1? It's a really important rule. Anybody? It's the only rule. There's only one rule. Great rule of organic chemistry number 1 and number only. What do you do when you have no idea what you're doing? When you're confronted with your reaction. Draw the minor resonance structure, right? The major resonance structure doesn't make it obvious that this carbon is negatively charged, but the minor resonance structure does. So this is your nucleophile for the nucleophilic acyl addition. And you have to do these two steps, the SN2 reaction and the removal of that proton with strong base, before you can get to having the nucleophile that's going to act to the carbonyl group. It doesn't really matter if you show the reaction from the phosphorate or from the ylid. All that's going to change is where your arrow starts. This is going to add to a carbonyl compound. Let's use that aldehyde from chapter 18. And again, the minor resonance structure of the carbonyl compound tells you where the electrophile is. Right? This is the electrophile. So this is a Lewis acid-base reaction where we're taking the nucleophilic carbon from the ylid and attacking the electrophilic carbon of the carbonyl, or you can show it from the phosphorate by just starting your arrow from the bottom. It's this pi bond that's going to be doing the attacking. So regardless of which of those you choose, we're going to get the new carbon-carbon bond, right? This is going to be a carbon-carbon single bond at this stage. You're going to get the O minus, and you've got the hydrogen from your aldehyde. This is called a beta. Because there's a compound called beta-medium that's made that's analogous to this. So it's got an oxygen minus and a phosphorus positive. They're not adjacent, so it's not an ylid. But they are close enough to each other that they're very likely to interact to form a four-member ring. It's almost resonance. If I drew that oxygen here, so that all I was moving was the pair of electrons and I didn't have to move the nucleus at all, then it would be resonance. Right? Resonance structures move only electrons, not nuclei. But because I drew the oxygen up there, I'm going to show this as equilibrium instead. And this is called an oxophosphatane. It's got a four-membered ring. So it's not that stable. It's relatively sterically hindered. So step 3, right? Step 3 is the key step. That's the actual nucleophilic acyl addition. And your challenge when you're doing the Wittig reaction is not to try to do the nucleophilic acyl addition until you get to step 3. You have to do the SN2 reaction to form the phosphonium salt first, and then treat it with n-butyllithium to make the ylid. Then you can get the carbonyl and let the carbonyl play. So step 4 is simply ring closure to form the oxophosphatane, and that's not very stable. So that is going to spontaneously react to form the very stable phosphorus oxygen double bond, and also form the carbon-carbon double bond in the process. This is driven by the very strong phosphorus oxygen double bond. And it doesn't really matter in this case because we're dye-substituted on both ends, whether I show the arrows going like this or show them going the other way. But in general, whichever carbon is better able to stabilize the positive charge, that's the one you want to show this bond coming from, because it's going to build up a partial positive charge on that carbon in the byproduct, and it's going to build up a partial negative charge on the other carbon. Right? But it just decomposes to break the four-membered ring and relieve ring strain. So it's really not that challenging, and I don't know why I had so much trouble with it when I first got introduced to the Wittig reaction. It's just 5 steps, which is fewer steps than a lot of other reactions. Right? SN2 reaction, that's easy. Everybody knows about an SN2 reaction. Deprotonation next to a positively charged phosphorus is entirely logical, right? Because you have a positive charge there. Makes sense that a negative charge adjacent would be pretty stable. Once you have this negatively charged carbon, entirely logical that it could act as a nucleophile to do a nucleophilic acyl addition reaction, and then getting a negatively charged oxygen and a positively charged phosphorus together is pretty obvious. But once you have a four-membered ring, four-membered rings aren't very stable. Decomposing that makes sense. So it shouldn't be a difficult mechanism, but for some reason it is. So how would you write this out if you wanted to write it out kind of as a synthesis? And there the challenge again is the carbonyl compound is not actually involved in the first 2 steps. So the way you would write this out is you would start with the alkyl halide. Step 1 would be to add triphenylphosphine. Step 2 would be to add N-butyl lithium in hexanes. Step 3 would be to add the carbonyl compound. In this case, the aldehyde. And that proceeds, right? It makes this intermediate. That intermediate closes to form the four-membered ring, and then that four-membered ring decomposes. So the challenge is that the carbonyl compound, which is the molecule you're probably most focused on, only appears right at the end. The first 2 steps have nothing to do with the carbonyl compound. Pretty straightforward. Not great, though. It's Z-selective, but you're going to get the E isomer as well. And you often only get like 60% stereoselectivity. So it's pretty crappy. And then you have to get rid of this heavy organic soluble byproduct and throw away a lot of your mass. Triphenylphosphine is relatively inexpensive, but triphenylphosphine oxide is not completely environmentally benign, and it's kind of a pain in the ass if you generate huge quantities of it, if you're running large scale reactions. So we can solve those problems. Questions on the Wittig mechanism. What are the chances that at some point you're going to have to either reproduce the Wittig or the Horner-Emmons mechanism on a quiz? If you were a gambler and you had to put money on the Wittig mechanism or the Horner-Emmons, which is what I'm going to show next, mechanism will appear on a quiz sometime, how much would you bet?
The chances were 100%.
They are
Wow,
100%.
quiz.
You'd be safe. You can bet your house on that. One of those 2 mechanisms is going to appear somewhere on a quiz or on an exam. You're going to need to know the Wittig reaction. The better modification of the Wittig reaction starts with a different compound. It starts with a phosphite instead of a phosphine. So, first step, knowing what the phosphite is. What is a phosphite? A phosphine is R3P, And a phosphite is R-O3P. So it's 3 alkoxy groups instead of 3 alkyl groups. The most common phosphites that are used are the methyl and the ethyl. And you might recognize this as an ester of H3PO3, which is phosphorous acid. So it's basically H3PO3, but instead of having OH groups, we have a whole R group. So it's a trimethyl ester of phosphorus acid, and that's a phosphite. So the first step is the same, pretty much. It's to take the nucleophilic phosphorus lone pair, a little bit less nucleophilic because it has 3 electron withdrawing oxygens, pulling electron density away, but still a good nucleophile, and react it in an SN2 reaction with an alkyl halide. And just to avoid introducing too much complexity, let's use the same alkyl halide. So we're going to use bromoethane. It's a nice SN2 reaction. And it generates a salt. And it goes with inversion, not that that matters, but it does. Right? So nothing different. But there's a reason why I drew this methyl group out like this. And I put the bromide ion that got displaced right there so that it's on a line with this carbon oxygen bond. Because this O is an excellent leaving group. So this whole piece can act as a leaving group for a second SN2 reaction where the bromide ion, right, which is a good leaving group and a good nucleophile, pushes out that oxygen to form bromoethane. Form. It's another phosphorus species. It's got a name. This is a phosphonate. It has 2 OR and 1 R. Attached to a phosphorus oxygen double bond. So it's phosphorus 5 as opposed to phosphorus 3. Right? The phosphite is a phosphorus 3 species. It's got a lone pair of 3 things attached. Now we've got a phosphorus oxygen double bond. So that's phosphorus in the +5 oxidation state instead of the +3 oxidation. So it's 2 successive SN2 reactions. And this sequence of 2 SN2 reactions is called the Arbusal reaction. So you do the Arbusov reaction to generate the phosphonate, and then the phosphonate is what's going to go into the Horner-Emmons reaction and act as our nucleophile for the nucleophilic acyl addition to the carbon-oxygen double bond. You'll notice that there's no carbon-oxygen double bond yet, right? We haven't done anything with the aldehyde, right? So there's no nucleophilic acyl addition until after we've done the Arbusov reaction. So that probably explains why we generally start with either the methyl phosphite or the ethyl phosphite, because we want this to be either primary in the case of ethyl or methyl, so we get a really good SN2 reaction And you can do this with alkyl iodides as well, because iodide is also an excellent leaving group and then turns around as an excellent nucleophile extent too. So two SN2 reactions, one happening on the alkyl halide and then one happening on this intermediate phosphorus species to generate the phosphorus oxygen double bond. So what does that look like to you? That phosphorus species, phosphate. What would you estimate for a pKa for those hydrogens? If you had to estimate.
20-ish. I'm not sure what the phosphor does to it.
So if this were carbon, right, it would be around 20 to 22. It's not carbon, it's phosphorus, but the phosphorus oxygen double bond is also able to stabilize a negative charge by resonance. So you might guess similar to CH2 adjacent to a carbonyl. Maybe even a little bit more acidic because of the electrophilicity or the electronegativity of phosphorus versus the electronegativity of carbon, right? Phosphorus is a little bit more electronegative than carbon. So maybe it pulls electron density away and stabilizes it a little bit more. The key is, because this pKa is quite a bit lower, right, quite a bit more acidic than when you had alkyl groups here and no phosphorus oxygen double bond, you can take this off with milder bases. Which is potentially useful if there's something else that's base sensitive somewhere in the molecule. So what would be a good base choice, do you think? Maybe a little hint there.
Water.
We've got OCH3 groups attached to the phosphorus. Let's use OCH3 as our base. Right. That way, if the OCH3 group attaches itself to the phosphorus, nothing really happens because it can come back in and kick out another OCH3 group. So we avoid what's called transesterification. By using the conjugate base of the ester. Right? So this is an ester as well, of phosphonic acid. And that's very common that when you're working with an ester, you use the conjugate base that corresponds to the alkyl group as part of the ester. So that's going to come in and take off that hydrogen. And I'm going to show it in the more stable resonance form that has the negative charge on phosphorus. And then it's the salt. So the
Avoid.
What's that?
The word after avoid. Trans what?
Transesterification.
Okay, thank you.
So basically, we have a methyl ester here. We want to use the same base so that we'll always have a methoxy group. We want to introduce an ethoxy group and have multiple species. So now we have something that's analogous to that phosphorate. And it's resonance stabilized. So in the one resonance structure, it's analogous to the ylide, it has a negative charge on the carbon. In the other resonance structure, it's analogous to the phosphorane. And you can make it look even more like an ylide. If you draw the minor resonance form of the phosphorus species, it looks like that. So it's effectively a positively charged phosphorus and a negatively charged carbon adjacent to each other. It's just that in this case, the carbon, or the phosphorus rather, has just a delta plus on it because of that polar phosphorus oxygen double bond. So that can add really readily to carbonyl compounds. Right? So we've done 3 steps before we even bring in the carbonyl compound. The carbonyl compound comes in step 4. So now we can add this. And if you wanted to, you could have shown it from here as well. You can show the mechanism for either resonance structure. Just by changing your arrows a little bit, so we reform the phosphorus oxygen double bond. So in one case, I'm starting my arrow from a lone pair, in the other, I'm starting it from the pi bond, but it's functionally equivalent. So this is ylate, right? This is basically ylate. It looks like the ylide in this resonance structure. It looks like the phosphorane in this resonance structure, and it kind of just looks like an enolate ion in the resonance structure that I've shown on the right. This reaction, by the way, is not in your textbook. So we formed our new CC bond here. And once again, we've got a negatively charged oxygen and a significantly positively charged phosphorus kind of near each other in a 4-membered ring. So this intermediate is analogous to the beta ketene, except that we have a phosphorus double bond oxygen instead of a positively charged phosphorus. And then we're going to close up the ring in step 5. To generate a pentavalent phosphorus now. And a 4-membered ring. Negatively charged intermediate. So what's this analogous to? What phosphorus species from the Wittig reaction does this look like? We had something that was analogous to the phosphorine. We had something that was analogous to the ylide. We now have something that's analogous to the betaine.
Oxophosphane? Phane? I don't remember.
The
Phane, I think?
The oxophosphatane, right? So this is analogous to the oxophosphatane, except now we've got a pentavalent phosphorus and we got this O minus. You can imagine that this would actually be pretty good at pushing out a pair of electrons to form the CC bond, and that oxygen on phosphorus could generate a minus charge. So step 6 is to kind of decompose, relieve ring strain. In this case, we get the E isomer, and we get a very good yield of the E isomer, very little Z. And we get a water-soluble phosphate salt. Right? This is the dimethyl ester of phosphoric acid. Better atom economy, because we're working with methoxy groups, and methoxy groups weigh less than a phenyl group, so we're throwing away less mass. It's pretty safe. I mean, you don't want lots of phosphate in the rivers and things, but it's not toxic at any level. Very easily washed away in the water layer, so we've solved our purification problem, and we've gotten a much more selective reaction. So the first two steps of this pathway are called the Arbusov reaction, those two successive SF2 reactions to generate the phosphonate. And then you've got a four-step mechanism that's similar to the Wittig reaction, where you deprotonate, but this time with a milder base, do the nucleophilic acyl addition, and then after the nucleophilic acyl addition, we close up the ring to make the 4-member intermediate, and then relieve ring strength. You'll notice the way I showed these arrows. It is important in this case to show the arrows in the right direction, because this oxygen is going to become a minus. So you have to break the carbon-phosphorus bond, right, with this lone pair to form the new CC bond, and then the carbon-oxygen bond here is the one that breaks the negative charge on the oxygen. I think we're out of time. I'm maybe even a little bit over. Sorry about that. Questions on this? Obviously, this reaction is in the pre-recorded videos as well. So what I haven't covered in chapter 17 yet is I didn't do the mechanism for the Wolff-Kishner reaction, but there's a video on that pre-recorded. And we didn't really talk about cyanohydrins yet, or the Baeyer-Villiger oxidation. So I'll pick those topics up. Problem set number 4 from chapter 17 is the Baeyer-Villiger reaction. Just put that on pause, wait. Thursday's lecture is the aldol condensation, which is super important, but there'll be time on Thursday for me to also go over some of those reactions from chapter 17 that I haven't picked up. So what's the quiz on Thursday?
One of those mechanisms.
Probably one of these mechanisms. Good choice, right? So make sure you go through the Wittig and the Horner-Emmons and the Arbusal and understand the steps and the mechanisms and what the various intermediates look like. We good? And then hopefully we'll actually be in person on Thursday because it won't have snowed again. We'll see. I'll leave that up for a while. I'm going to save the video and